Oh, before I move on to exercise, this might be an excellent example of, because you guys are math major mostly, this is something that you will understand and other students might not. So here's an example. Here p is a polynomial, and x to the p is a polynomial with coefficients. Where do you think its coefficients coming from? Polynomial x to the p, fp, right? Polynomial from fp. All right, what is fp? Finite field, how many elements are there? P elements are there. That's our number system. Q, Z, and R, and C, those are big. They're infinitely many number. We only have P numbers here. That's what this Fp is, right? So 1 times x to the p, where 1 here in front of x to the p is the 1 in the finite field. And Q is this polynomial x. X is not representing an element in Fp. This formal name for that is indeterminate. Determinate. Did I pronounce it correctly? Indeterminate. This is a letter, and it is an object in mathematics. Not like x is representing some number. That's how it's usually introduced to, kids, that what is x is going to be, that you represent a number. At some point in mathematics, x becomes just a mathematical entity. X is x. X is a letter. Okay? So that's an entity. So that's what this x to the p is. X is English letter, not representing any of the Fp. So polynomial is a new structure of adding and subtracting and multiplying. That's what that is. So that's what I mean by polynomial. And the second thing I would like to, so these two polynomials are different, right? You think this polynomial two different? Different degree. This one has a degree p, that one has degree 1, right? And the coefficients are the same, but different degree. So here's a function I'd like to define from finite field to finite field, given by f of x raised to the x to the p. Okay? So here x really represents an element in Fp, right? It is telling you that if I give you an input value x in that finite field, and you're going to raise it to the pth power. That's what this function is representing, right? And it's given by polynomial. The function uses polynomial, but this function is not polynomial. G is Fp, also given by, not also, but it can be a similar structure, x. What kind of function is it called? It has a special name. I give you an input x, and your output is x itself. Identity function. It has a special name. It does do nothing. I think the reason they call it identity, it has multiplicative structure when the functions are composed to each other. I think that's where they come from. Like identity matrix, right? What is the real definition of the matrix? It's really the map. If I give you x and y and you create another x prime, y prime, things like that. So this is functions, right? What are these? These are polynomials, different objects. But can you say this function f of x is equal to g of x? Can you say that? F of x is given by x to the p, g of x is given by x. Is this function f of x is equal to g of x? You wouldn't say yes if our function has a domain rational number or integers, right? That's not true. These two functions are true. If this is an integer going from z to z, what is an example these two function values are different? Instead of fp to fp, if it's z to z, you can probably find many examples. But is this true for all x in the finite field? No matter what you plug into this f function and g function, you get exactly the same output. Who can explain that? For example, if I give you 2, f of 2, right? F of 2, and that's the 2 to the pth power. Is that right? And the g of 2, what is it? 2, by definition. Is 2 to the p is equal to 2 in the finite field, right? We're in the finite field, remember? This is in the finite field. So in finite field. Is that true? Anybody? It depends on what P is, but it turns out, yeah, it makes sense. But when P is 1, yes, it's true, right? When P is 2, doesn't seem like it's true, right? 2 to the second is 4 equals 2, but it is all happening in the finite field. So think about, P equals 2, and what is 2 squared? Well, 2. Let's do P equals 3. That's more interesting. P equals 3. What do you get? 2 to the third, right? That's 8, but in the finite field, you don't write 8. What do you write? 8 is 2 mod 3, right? So is that 2? Correct, right? Correct. You want to try 1 is obvious. Mod 3, there's 0 and 1 and 2. Okay? So I want you to go ahead and try P equals 5 then. See what you get. P 2 raised to 5, what is this? 32 is not an element in FP, so you reduce it mod 5, which is 2, right? So you find this a 32 modulo 5, so back to 2 again, right? But that's only x equals 2. You have to try 3, you have to try 4, and you have to try 0 and 1. 0 and 1 is kind of obvious, right? 0 raised to p to the power. So it is true, actually. This statement is true. This function, given by different formula, completely different formula, there's no way to factor and everything, make it equal to each other. It's exactly the same function, right? This is an excellent example from which you can distinguish the notion of function from the notion of formula, right? The simpler example is that I think I've already introduced, whether it's in the finite field or it doesn't matter, there's two different formula. You immediately identify these two things identical to each other, but these are two different formula. One is you add first and square later, and the second one is more complicated. But you know the function values are exactly the same, right? But we also identify these two things as the same polynomial, though. As a polynomial, we identify this as the same polynomial, right? As an algorithm, it's different. The process of a computation you go through is different. As an algorithm, different. Polynomial is the same. As a function, is the same, right? And here, if you look at this example, this is a polynomial, and this is a different polynomial. Different algorithm, we do different things. As a polynomial, it's a different degree, it's different. But as a function, they're exactly the same output. So if you really go back to your proof book, look it up, what is a function? Function only cares about what is the input and what is the output. Function does not distinguish what you do in between. If this is my input, that's my output. If that pair is exactly the same, we call these two functions are the same. So maybe if you're confused by this notation here, I know what you mean by this, but I don't quite disagree. That means you didn't quite understand the meaning of a function. Function only cares about what goes in or what goes out. Doesn't care what happened in between. So it makes sense, right? So that's why these two things are the same function. But as a polynomial, it's different. Okay? Formula versus function is different. All right, let me go and copy this.